Welcome everyone to the second lecture of this section 13 of this afternoon, Combinatorics. I have the pleasure of introducing our second speaker, Igor Pak. Igor got his PhD at Harvard under the guidance of Percy Diaconis in '97. Since then, he's been at MIT, Yale, University of Minnesota, and since 2009, he's full professor at UCLA. Igor is a mathematician of broad interests, so he has done work on several subjects, such as discrete and polyhedral geometry, algebraic, enumerative, and geometric combinatorics, random walks, asymptotic and probabilistic group theory. Today, his lecture is on complexity of combinatorial sequences.
Thank you.
You're good.
Thank you so much. Can you hear me? Yeah? All right. Thank you for coming to this lecture. Thank you, the organizers, for inviting me. It's a great pleasure to be here in Rio. It's nice here. And I'm going to try to give a friendly talk. I'm not going to try to overwhelm you. It's going to be as simple as this sequence. This is a sequence of Catalan numbers. And I'm just going to talk about combinatorial sequences. OK? Everyone OK? So the title is about complexity of combinatorial sequences. And first, I want to tell you what are the sequences I'm considering. And that's already a problem, because if you look at online encyclopedia of integer sequences, you see that there are over 300,000 sequences there. And if you look at what Sloan and Plouffe wrote about which sequences they include, they say that, well, we include all interesting sequences, basically everything that people want. And that, of course, not what I want. And you can see from Richard Guy's review of online encyclopedia that, in fact, it includes all kinds of sequences, including hard, disallowed, and silly sequences. And I don't want to consider them, but how do we distinguish? That's already a problem. So let me show you a few of those sequences, and let's see if you can figure out what are the silly ones. So the first sequence is just the number of groups of order n, number of finite groups of order n. Then there are, these are just a few of the top 100 sequences. As I said, there are 300,000. I'm not going to list them all. Especially, let's see. So this sequence P of n is especially nice. This is a sequence of number of partitions of n as a sum of integers. That's very a beautiful sequence. Here is a sequence of Fibonacci numbers. So here is a sequence that without help, usually when I give talks, I don't write this. So this is a sequence of stops of the New York City subway line. So that's one of those silly sequences that you can find. So it starts at about, I see you pointing, this is 4th Street, 14th Street, etc. And this is 4th Street is NYU, 116 is Columbia, and I decided not to list anything beyond that. That's how it works. So there are some sequences which are actually quite difficult to compute. For example, number of graphs on n vertices, that's number of graphs after isomorphism. That's much harder to compute than some of other sequences that you see here. So I'm going to talk about what's a nice sequence a little bit later, but let me just give you a few examples as a flavor of what do I mean by what kind of combinatorial sequence we want. I'm just going to denote all sequences AN, and they're going to be combinatorial sequences of the type, for example, it's number of triangulations of n gone, or number of domino tiling of an n by n gone. So usually there's just one parameter n, and we want to understand these sequences. So some of these sequences are easy to compute. There is just direct formula here. Some of them can be computed in polynomial time. For example, number of label graphs on vertices, there is a recurrence relation here. But number of triangulations of an n by n grid, we don't actually know how to compute efficiently. Okay? That sounds like already a basic problem that we cannot do. And that's what I'm going to be talking about. So there are two main questions. The first question is there a formula for the sequence? And usually the way we phrase it is in terms of generating functions. So what we do is we take a sequence, we take a generating function for the sequence, and we ask is there a formula of some kind for either numbers or for the generating functions. And a question that's very interesting and very close to my heart is whether numbers can be computed efficiently. So some years ago, Herb Wilf sort of started the subject by suggesting that number of labeled graphs and vertices is hard to compute, whatever that means. And this is still quite a bit open, but that question is the kind of question that really sort of started this subject. Is everyone okay? All right. So what I'm going to do is, what I usually do in these cases is I'm going to start with the simplest sequence of all, and this is the sequence you've already seen. This is a sequence of Fibonacci numbers, and there are several formulas for the sequence. This is what people usually think of the definition. This is somewhat rarely used formula. This is representing Fibonacci numbers as a sum of binomial coefficients. It's actually extremely useful as a formula because that allows you to prove that Fibonacci numbers are irrational. You can do it in other ways as well, but that's extremely useful. This is actually a little bit wrong with the sign, but this is a formula for the Fibonacci numbers in terms of golden ratio. And that tells you that the golden ratio to the power n divided by square root of phi of n is really the leading asymptotic term for the Fibonacci numbers. And finally, we have a formula in terms of matrices. So nth power of this nice matrix is actually gives you a pair of Fibonacci numbers. And that's, from application point of view, is the most useful formula of all, because that's what allows you to actually compute Fibonacci numbers extremely fast by doing sort of repeated squaring. Okay? So what this simple selection of formulas suggests is that there is no one good definition of a formula. Different formulas are good for different things, but in particular, already the definition of Fibonacci numbers allows you to compute Fibonacci numbers in polynomial time. All right. So here are a few examples of more complicated formulas, and there's even an argument whether some of them are formulas at all. So one is a rather standard college level result about number of derangements. This is a number of permutations without fixed points. It turns out that the number of them is the nearest integer to the n factorial divided by e. And if you think about it, that's already unclear if that's a formula at all. Because how would you even compute that? E is not a number that you would, it's not like 3 that you can just divide and be done. E is a more complicated number that you need, in order to divide, you need quite a bit of precision when you do that in order to understand the nearest integer. And so that already from computation point of view requires some effort. This is a standard generating function for Catalan numbers. It's not the best formula. You've seen Catalan numbers before. The Catalan numbers have a beautiful formula in terms of binomial coefficients. However, that formula does allow you to compute Catalan numbers. It just gives you a somewhat slow algorithm to do that. This is a formula for Euler numbers. It's in terms of coefficients in the power series. And this power series can be defined as a solution of this differential equation with some initial conditions. And if you think about it, it does allow you also to compute Euler numbers. It's just not a super efficient algorithm. Okay, we can do better. And it gets even worse. So this is really a really complicated formula for number n to the n minus 2, number of trees and vertices. So if you look at this generating function, that's a really complicated generating function. You don't want to understand that. Okay? So In some sense, this is completely equivalent to the definition of a tree, it's a recursive definition of a tree, and it's a terrible formula for the computational purposes. This is Euler formula for the number of partitions of n, and Euler proved it, but it's not particularly efficient. It's not very useful at all for the purpose of computing the number of partitions of n. And pi of n is the number of primes less or equal than n. This so-called formula, I copied it from some book. It's no good formula at all. It's basically a really complicated way of testing whether whether k is a divisor of n at all. So we're basically summing the number. So we're basically summing all kinds of divisors, and that's you can do much better than that. So the point is, some formulas are better than others, and we need to understand what we want. And a rather natural way of approaching this is from a computational point of view, is just to say that sequence can be computed efficiently if there is an algorithm which computes an in time polynomial in n. So, for example, Fibonacci numbers, Catalan numbers, derangement numbers, etc., can all be computed in polynomial time, and you can just go home and figure out each of them. For example, Fibonacci numbers, you can do it straight from definition. So here is a very small collection of rather non-trivial results in the subject. They're more or less ad hoc results. So, for example, number of connected irregular graphs and vertices can in fact be computed in polynomial time. This is not obvious. This is not easy at all. And in fact, it's true, of course, for k-regular graphs, and you don't need the word connected here. I'm just not writing all the possibilities. But that's a rather difficult result in the subject. So for every fixed k, number of connected k-regular graphs can be computed in polynomial time. This is due to Gestalt. Another result is number of non-isomorphic trees on n vertices, or, for example, the Kelly sequence, number of partitions of 2 to the n into powers of 2. These are so-called binary partitions. That can also be computed in polynomial time, and each of those results is sort of an ad hoc result which uses deep properties of the underlying combinatorial objects. Are we okay so far? Okay, I see there are no questions. So. So let me move on then. So here is something. Here is a quote that's a rather famous quote by Karl Popper, which says that it's not enough to have positive results. That's not a good theory. We really need negative results, otherwise the theory is rather empty. Okay, and that's what I really think is the most important problem in the field, is how do you prove negative results? And negative results are difficult to prove, and in fact, there are really, Wolf conjecture is an example of a result that should be negative, but I actually personally don't believe that it's negative at all. It might be possible that the number of non-isomorphic graphs can be computed in polynomial time. But I want to discard some examples. For example, sequences which grow very rapidly. It just takes too long to write. We can't do it in polynomial time. Or some problems are really open problem mathematics in disguise. For example, a question whether you can write a sequence of all prime Fibonacci numbers. That's an open problem. We don't know if it's an infinite sequence at all. So I want to consider natural combinatorial problems, which one would believe should have a negative answer, and there are not that many of them. If you start thinking about it, you only get positive results in the literature, or almost always do. So one conjecture that I proposed is number of self-avoiding walks in the plane with n steps starting in the origin. I don't think that can be computed in polynomial time. Number of self-avoiding walks is just too hard of a sequence. However, unfortunately, there's just no way I can even approach this conjecture. It's sort of funny to state a conjecture for which you can't approach at all. And this is where I think one should switch from computer science back to combinatorics. So there is a famous quote by Stephen Smale that P versus NP is a gift from mathematics to computer science. But not all gifts are actually good for you. Sometimes you should just like kind of refuse the gift. And so this is a famous painting which shows the kind of gift that you really don't want to get. And that's maybe the only joke in the talk. Enjoy it. Okay. So I'm serious that one should go back to combinatorics, and because complexity might not be a way to go. So what I want to do is I want to sort of tell you how one can approach these problems from old traditional enumerative combinatorics. And one way to do that is to say that, look, let's just consider a classification of integer sequences, and the way we do it is by looking at the generating functions. And the generating functions, there are a bigger and bigger class of generating function. So for example, rational generating function, a ratio of two polynomials with integer coefficients. Algebraic generating function is generating function which satisfies some polynomial relation. You see, I hope this is not too small for you to see. So one standard example, Fibonacci numbers is a give rational generating function. Catalan numbers give this algebraic generating function. You've seen it before, actually. Very important definition of define a generating function. These are generating functions which satisfy ordinary differential equation of case order. So one standard example is the number of involutions in the symmetric group. Number of involutions in the symmetric group satisfies a rather nice recurrence relation, which you can immediately see actually because either the first element is moved or not. If it's not moved, then the number of involutions on n is the same as number of n minus 1. If it is moved, it's n minus 1 times n minus 2. Now, it is a nice exercise to realize that every time you have a polynomial relation like that, that gives rise to a differential equation of this kind. And therefore, this class of sequences is called pericursive sequences, but all their generating functions are exactly defined generating functions. And the somewhat rarely used but very important class of algebraic differential equation is a class of generating functions which satisfies an algebraic differential equation of finite orders. So these are derivatives, and we have a polynomial which is equal to 0, polynomial in k plus 2 variables, its first derivative, second derivative, etc., and the underlying variable t. So one example is number of alternating permutations. This is a number of permutations which first element less than second, greater than third, etc. And that satisfies algebraic differential equation. Notice that the product is what makes it algebraic differential. If it was a sum, that would be defined. And I wanted to give one complicated example. So recall our number of integer partitions of n. This is due to, it's sort of never been written by Jacobi. So Ramanujan was able to use Jacobi's idea to prove that this sequence, to be precise, generating function with sequence satisfies algebraic differential equation, which I wrote to you over there. It's people usually don't write it explicitly, and but when you write it, you see how complicated this is. Okay, even this classical sequence of number of partitions of n. Okay, so this is the only technical slide. I hope you memorized it, and because we're going to move on. So the general philosophy is the following. Pericursive sequence, I told you, you can just compute them easily because of the recurrence. But one should think of, and ADE sequences are actually, there is an inclusion, rational algebraic pericursive also defined and ADE. And it's a really easy proposition to show that ADE sequences also can be computed efficiently. Straight from the definition, straight from the algebraic differential equation. So now, if one has a sequence which you consider to be hard, which you don't think can be computed efficiently, the best way is to start studying it is by showing that it's actually not definite or not AD. That's already super hard in many cases. Because if it was, if it was defined, then we could compute it efficiently. So if we believe the sequence is hard, then it's not going to be defined and it's not going to be AD. Okay? So that's the philosophy. And it turns out that many combinatorial sequences are nice and they fall in these classes, as I mentioned. However, for hard sequences, it's also hard to prove. Even that is hard to prove already. And that's what I do. Okay? And that's what many people in the field are actually doing, trying to understand what's going on. So now let me mention some results which are non-combinatorial, just so you can see how hard can that be. So this is a famous result by Jacobi that that the theta function satisfies algebraic differential equation. That's over 150 years old. And here is a somewhat more recent result by Lipschitz and Rubel, which says that basically generating functions which have which are 0-1 sequence with large gaps cannot satisfy algebraic differential equation. That's already quite non-trivial. You cannot, and that involves quite a bit of technology. So I just chose 2 to the n as an example. You can have any exponential function here. However, this should be countered with a conjecture instead of n squared. Let's just put n cube. There is no way. It's been open for a really long time whether this sequence, whether this generating function satisfies the algebraic differential equation. And it says, I tried. This is a terribly complicated conjecture. The way to think of this is as complicated as other conjectures in number theory. What this basically says is there are nice results about ways of writing a number as a sum of squares, because when you raise this generating function to the powers, you get coefficients to be number of ways of writing an integer sum of squares. And this conjecture is saying there is nothing good about writing an integer as a sum of cubes. You just cannot do it. Okay? There's no good formulas for that at all. So here is a theorem that's much more approachable. So this is a generating function for primes. We just look at generating for primes, and then one can use asymptotic, careful asymptotic results for primes to show that this generating function is actually not defined. And this should be countered with this conjecture. So we don't actually know whether it's AD at all. I don't believe this is as hard as this conjecture. However, we just don't have tools to solve this. There is just no way to do it with current technology. So luckily, this is not particularly combinatorial, and I'm just going to move to one class of sequences that I particularly like, and those are walks and graphs. So what we're going to do is we're just going to fix a graph and fix a vertex and consider the number of walks in this graph of length n. This should be from O to O. Okay? So the number of walks of length n. So for example, if you're going to look at number of walks in this graph of length n, you get Fibonacci numbers. In this graph, this is sort of half line starting at the origin, going to the plus infinity. Then the number of these walks is going to be Catalan numbers and so forth. And that's a beautiful class of examples. And in these cases, you get a lot of integer sequences. So for example, one can consider regions as a grid, or one can consider Kelly graph of a finite group, but even better, infinite group, with a generating set and with a finite generating set. And in this case, it's called co-growth sequence. So this is the most popular case when you consider region in the grid, and there are actually dozens and dozens of papers covering that case, and I'm not going to talk about that at all. These are results by Bousquet-Milieu and her co-authors, and those is just a fantastic family which will occupy all my time if I start talking about those results. So what I'm going to do is talk about groups for now. And I want to mention a few results. So if a group is an abelian group, if we're really walking in the grid with a finite set of steps, then the co-growth sequence, so remember this is a number of walks of length n which start and return to the origin. So in that case, it's always, no matter what set of steps you take, this sequence is always going to be pericursive. So the corresponding generating function satisfies ordinary differential equation. And it was observed by Fürstenberg that if you so if you, this is, I'm not saying it right. Yes, so if you're looking just in the plane, it's, the sequence is going to be 2n choose n squared, and that's already not an algebraic sequence. That's not particularly obvious, but that's not super hard to do. However, this should be paired with the result about the free group. So when you take a standard generating sets and a free group, the corresponding co-growth sequence is going to be actually algebraic. So somehow free group is actually simpler than Z2. Okay? In the sense I'm describing it. All right. So here are a few recent results for the co-growth sequence, number of walks of length n. I just chose this because they counter each other in some, complement each other in some way. So if you have these bump-slack solitaire groups, which can be defined in the following way, and you pick those generators x and y, just like in the definition of bump-slack solitaire group, but have this n. So you see then the co-growth sequence is actually going to be pericursive. And the way to prove that is by providing explicitly the generating function. So what these authors did is they found explicit form of the generating function and showed that it satisfies a differential equation. There is no obvious way to do that straight from the definition. And this should be countered with my recent result with Scott Garabrand, where we show that the co-growth sequence is actually not pericursive for a large class of groups, which includes bump-slack solitaire groups BS K1, where K is greater or equal to 2. So as you can see, it's sort of hard to look at the group and tell what exactly is going on, and those results hold for any generating set that you can begin with. And they include amenable linear groups of superpolynomial groups and groups of weakly exponential groups. And those two classes are actually recently generalized by Bell and Mishna just about 2 months ago, who showed that in a more general case, the sequence is not pericursive for all amenable groups of superpolynomial growth. So that includes those two classes. So in fact, when I say to understand this, this is just amenable groups which are not virtually nilpotent. That's how you can understand it using Gromov's theorem. And so what do you do to prove that? So all those negative result use essentially the same lemma which is the best result we have, and that's an asymptotic result, which is saying that if you have a pericursive sequence which grows at most exponentially, then the asymptotics is actually of a certain very particular form. There is an exponential term, polynomial term, log n term, and the constants satisfy certain algebraic condition. And so this result is what I call a lemma is actually a combination of many results by analysts, but we use it as a just black box. What you do in each case is essentially find in the literature or prove from scratch a result about probability of return of the random walks on that group, and then convert it into co-growth sequence, and just observe that it's not going to satisfy this asymptotic condition. So this effectively reduces the problem, the combinatorial problem, to a probabilistic problem. Many of them are solved already. All right. So let me move on. So now what I want to talk about is a family of results which are actually not of this kind. Using asymptotics is terrific when you have them, but what happens when you don't? And so I'm going to mention just briefly two results. So we actually were able to find generating sets in the free group, so that, remember, Heyman's result says that there is a generating set for which this is algebraic. That's stronger than pericursive. And we showed a few years ago that one can have a generating set so that the co-growth sequence is not pericursive. And in fact, recently we showed that one can have a generating sequence so that the co-growth sequence doesn't satisfy algebraic differential equation. And that doesn't involve probabilistic asymptotic tools at all, and involves tools that I'm going to mention a little bit later, because I want to now switch away from groups to something that most combinatorials do, and that is consider permutations, and a lot of combinatorialists study various classes of permutations. So I'm going to look at permutations as 0-1 matrices, and I'm going to say that this 0-1 matrix, so one permutation contains another, if one 0-1 matrix contains another 0-1 matrix. So you can see there are 3 ones here which form these 3 ones. And then I'm going to say that the corresponding permutation contains this permutation 3-1. Okay? And similarly, it doesn't this permutation does not contain a decreasing sequence of length 4. So we would say that this permutation avoids permutation 4 3-1. And now we're going to ask the same question as we've been asking before. I'm going to fix a set of patterns here. And I'm going to denote by Cn of f the number of permutations in Sn which avoid this fixed set of patterns. So let me repeat. I'm gonna have a fixed set of patterns. And k is small. Think of small being 10 or 100. And now I'm going to look at a large sequence, number of permutations that avoid this fixed set of patterns. Okay? And the two questions I'm going to ask: is the corresponding generating function going to be defined? Is it going to be ADE? And can you compute this number as polynomial time? Those tend to be rather difficult questions to study, and there is relatively little has been known until very recently. So let me give you a really long slide, which I'm not going to read, which is basically justifying why considering this pattern avoidance is nice. So I'll begin with this is increasing K permutation, decreasing L permutation. And now Erdős-Zekers theorem basically says that for n large enough, there is no permutation which is going to avoid both of them. Okay? So either you're going to have a long increasing subsequence or long decreasing subsequence. So that's a classical result from extremal combinatorics. The second motivation comes from this result by McMahon and Knuth, separated by 60 years, which says that number of permutation avoiding any 3 permutation, for example, 1, 2, 3, and 2, 1, 3, is always going to be Catalan number. That's why I'm using Cn. Essentially, number of pattern avoiding permutation generalizes Catalan numbers in this sense. And in fact, there are lots of other sets of patterns for which you get famous sequences. For example, you get Fibonacci sequence, Schroeder sequence, and many, many other sequences. And in particular, there are few results that are known. So, for example, number of permutation avoiding 1, 2, 3, 4 is actually defined. This is a result by Gessler. Number of permutation avoiding 1, 3, 4, 2 has algebraic generating function and so forth. And let me mention a couple of very beautiful asymptotic results. One result is a famous result by Marcus and Tardish, which improved on Allot-Friedgut bound, which says that the number of pattern avoiding permutation, it always grows at most exponentially. That's a very important thing for us to understand. And another result is a more recent result by Jacob Fox, who says that if you take a random permutation pattern, then this constant in the base of exponent actually is rather large. It itself grows exponentially with k. So hope you're now convinced, or at least somewhat convinced, that this pattern avoidance is an important notion. And so let me tell you a couple of results that recent results that are important for us. And the first result is a disproof of Noonan-Zellberger conjecture, which I did again with Scott Garabrand. What we do is we say the following. There exists a set of patterns of a rather large permutation group and a rather large set of patterns. So in the paper, we have 10 to the 80,000 or 10 to the 60,000. But in reality, if you calculate carefully, 31,000 is enough. 31,000 patterns is not your friend. This is not something you want to write anywhere. So what we did is we were able to prove that there exists a set of patterns which we can explicitly construct so that the corresponding generating function is not defined. So it doesn't satisfy ordinary differential equation. And more recently, we were able to extend this result to a somewhat more complicated and much larger set of patterns so that the corresponding generating function does not satisfy ADE. And remember, there was a hope that this could be done using asymptotic tools. The hope didn't work out. Other people still have hopes that they can construct a much smaller set which would disprove Noonan-Zellberger conjecture. There is no hope in this case. We don't know how to approach proving that something is not AD by asymptotic tools at all, or by any tools other than the ones I'm presenting here. Okay. So a couple of historical notes. Noonan-Zellberger conjecture was actually stated by Gestel in 1990. However, Gestel was much more careful, and he didn't state it as a conjecture because he wasn't sure if it's right or wrong. And Noonan-Zellberger was very sure. However, Zellberger later changed his mind and conjectured the opposite. Conjectured that it's actually false, and the number of pattern avoiding permutations of just this pattern, 1, 3 to 4, is non-defined. That's still open. We don't know how to prove anything about that. So essentially what I did is I wrote to Zellberger an email asking him if he's willing to pay money if we disprove this conjecture. He said yes. He put a bounty of $100, and we disproved the conjecture, and he paid. Unfortunately, not to us, but to Online Encyclopedia of Integer Sequences. I would have liked the $100. So let me now explain computability implications of our work, which are not immediately apparent from the theorems. And however, so now somehow I'm taking the gift back, and I'm saying that yes, it's actually it actually does make sense from computer science point of view what we did. So this is just really corollary from the proof. What we show that the problem, so whether two sets of patterns have the same parity for the number of avoiding permutation is undecidable. Let me say it again. Suppose you have two sets of patterns, f and f prime. Okay? I'm going to consider number of pattern avoiding permutation of the first patterns and number of pattern avoiding permutations of the second pattern. Now I'm going to ask, are these numbers always do they always have the same parity? That's undecidable. That's a very strong statement, and people usually wonder what does undecidable mean. At least they should wonder. They rarely ask this question. And so one example, one corollary I tell them is that there exist two sets for every k. There exist two sets of patterns in the symmetry of size k, so that the first time when the parity changes is essentially any constructible function. Here I put as many 2's as I could, 2 to the k, just so that LaTeX still works. but in reality you can put a much larger function here. And that's amazing. That's basically saying that all these results, when you do experiments, you think something wrong for 2, 3, 5, 10, 20, 50, 100. That's just completely missing the point that eventually the parity somehow might change, and you're never going to know. So the second corollary is actually something I learned from Lazarovas, who taught me that this immediately implies that there exists a finite set of patterns. There exists a finite k, very, very large, but finite k, and 2 sets of patterns, so that the problem of deciding whether this number of pattern of permutation have always the same parity is independent on ZFC. That's quite amazing if you think about it, that you can embed the whole logic into just a fixed set of patterns. So now I really want to go back to Will's question and answer it in the best way I can. So these are complicated symbols here. If x is not equal to parity x, then there exists a finite set of patterns so that the sequence can be computed in time polynomial in n. Cannot be computed in time polynomial n. So here is what I mean. Think of that as some kind of complicated complexity theory assumption. This is not super complicated. This is basically saying that you should not be able to compute the parity for the number of 7-valent planar Hamiltonian graphs on n vertices. You should not be able to compute number of colorings, total number of colorings on some graphs on n vertices. So it's a rather involved complexity assumption. However, this is saying that if something that people in complexity theory believe is true, then there exists a set of patterns so that the sequence cannot be computed in time polynomial n. In fact, even the parity of that cannot be computed in time polynomial n. And that's, from my point of view, is what finally answers Will's questions from 82, whether one can describe a reasonable family for which one can provably show that there is no polynomial time algorithm to compute the sequence. And this is complicated. So I'm going to skip all the proofs and just going to say thank you. That's it. We're done.
Very good. Thank you very much. Are there any questions?
Can you switch back to something that is not there?
I'll switch to that.
Hello. So what's the complexity of computing this Cn of f when parameterized by the size of f and the largest pattern in f?
So I mentioned before, actually I didn't treat it, but when the size of the pattern is comparable with n, that's a sharply complete problem.
Yeah, but one is constant. It would be n to the k or n to the f of k or something like that, or 2 to the f of k times n? I
don't know, but there is no good bounds other than trivial bounds. So whatever is the most trivial bounds is the right one.
Okay.
Are there more questions? Okay, I don't see any. So thank you very much again, Igor.
Thank you.